they get there.
When they get held in the house.
I did two iterations.
I'll move this over here, get it out of everybody's way. Let's get started. Alright, sign-in sheet. That is not what I meant to do. I meant to turn the lights off, not the monitor off. Alright, sign-in sheet. Okay. Let's talk a little bit about scheduling. So you all turned in homework 3 today. My TA is still working on homework 2. So we'll get that back to you as soon as possible. If you don't have homework 2 by next week, like by Monday, I'll give you the solution to homework 2. So one way or another, that's a big assignment. Something's going to take a little while to grade. But if you don't have that by Monday, you'll get the solution. So that way you're good to go. Homework 3, you all are turning that in right now. Homework 4 just got posted. Now I want to show you something on homework 4 just because I thought about it right now. So homework 4 has 3 problems, okay? 3 problems. I want to show you something, okay? So here's problem 1. Problem 1 has, it's an unknown cross-section design, and we're going to finish our unknown cross-section problem today, but it has distributed loads and point loads. So you're not going to be able to use WL squared over 8 for these live loads. You can use it for the dead loads, but not for the live loads, okay? So that's something to keep in mind, all right? Now, number 1 is an unknown cross-section. Number 2 is a known cross-section, which you haven't done that yet, but we will. It's a shorter problem, but it's way different, okay? So it's a cantilever beam, and not only is there a uniformly distributed load, but there's a triangular load. So I'm going to tell you, WL squared over 8 ain't going to work for either one of those, okay? So just don't even try it, all right? Now, one thing I will mention, the guide that I gave you for moments for various situations, I believe triangular loads are there, but I would just be careful on using it, because sometimes the W that's there doesn't, it's not what you would think. Instead of it being this W, it's the entire magnitude. So just be really careful with using that with your units, and when in doubt, don't use it. Just determine what's your maximum moment due to the live load based off what we did last semester. That's problem 1. Problem 2, problem 3 is a slab design. We haven't done slab design, but you're going to see here in a second. We're going to see later on how problem 2 and problem 3, a known cross-section design and a slab design, are actually very, very similar. But that'll become clear when we get into that. Sound good? One final note, and this is on me. I sometimes take a little bit of time to add the videos to the playlist. But one thing I'll let you know about the recording software that I use, it automatically uploads the videos to my channel. So if I'm a little delayed in getting them on the playlist, they are there. In fact, the recording from today, if we finish class at 11, it'll be up there by like 11:30. So it will be on my channel. I just have to go on and add it. Sometimes I'm a little delayed on that, and I apologize. But I just wanted to make sure you're aware everything's there. Okay. Sound good? All right, so what we're going to do today is we're going to finish our design example with the unknown cross-section. Then we're going to get it to design with a known cross-section, which is by its nature easier. And we might start that example. I don't know if we'll get to it, but actually we probably will. We won't finish it, but we'll definitely get to it. Okay, so let's go back to the example that we were working on. Now let's just make sure that we're clear on the procedure. So we have a step-by-step procedure for design, and we started off with unknown cross-sections. So the first thing that we needed to do was compute the factored moment on the beam, which in order to do that, when you have an unknown cross-section, you have to assume the self-weight of the beam. So that's an assumption we're going to have to go back and check later. Now once you got your factored moment on the beam, so that's the load, that's how much the beam has to resist, you then determine, well, what is my required strength? What is the required nominal capacity in order to, for design purposes? And so you divide by 0.9, and that's an assumption. You're assuming that phi equals 0.9. Even though the beam has to have a phi equals 0.9, like you have to have that value according to ACI, determining whether or not phi equals 0.9 is a function of what the beam looks like. We don't have a clue what the beam looks like, so we're going to have to assume that right now. Next thing you do is you compute a rho value for design purposes. The 2 primary methods are to just guess a value, which this is a pretty good guess, or you can compute a value based off of a target strain value. Like I want the strain in the steel to be 0.01. So what reinforcement ratio is required to hit that strain value? And there's nothing wrong with that assumption as well, so either one works. Next, we compute a required BD squared. So compute a required BD squared based off the fact that you know what the material looks like, you know how much capacity you need, and you know what your reinforcement ratio is going to be. That tells you about how big the beam needs to be. From that and a target B over D ratio, you can figure out the dimensions of your beam, and then use rho BD to determine the area of steel required for the beam. And that's sort of where we left off last time, is we said, okay, let me go back to here. So here was our beam, simply supported beam, uniformly distributed load. So with this situation, we can use WL squared over 8 all day long. We had a 22-foot long beam with 1 kip per foot in dead load, 2 kips per foot in live load. Now that doesn't include the beam self-weight, so we had to guess something, came up with about 276.5. I'm going to write that down. I'm going to say that MU was 276.5 foot kips, and that's with an assumed self-weight. And I'm just writing that down for my purposes, because we're going to go back and check this here in a second, and you'll see that things changed. So we have the factored moment, computed a required nominal moment capacity, then computed a rho for design purposes, computed our required BD squared. And so ultimately what we left up with was this. We know the beam is 14 inches wide, we know the effective depth is 21 inches, and we didn't know what the steel pattern was, but we figured that out. The big thing, though, is that this is a trial section, okay, because we still have to go back and analyze it. The last thing that we did is we said, okay, here's how much steel we need, and then we went through this exercise, and we ended up selecting, what was it, 3 number 10s? Is that what we came up with, 3 number 10s? All right. So, in other words, here's our beam. We have 3 number 10s. We have this is 21 inches. This is 14 inches. And this is 24 inches. So, assuming everything works out correctly, that's the answer right there. That's the answer. Well, the question was design the beam. That's the design right there. That's how wide the beam needs to be. That's how tall it needs to be. That's how much steel we need to put into it. However, we have to go back and we have to assess that based off of our assumptions. So let me explain what that means. Okay, so step 9, this is the new stuff. So step 9 is analyze, and I'm going to call it trial section. And so for you folks in steel design, this should be somewhat familiar. And this is common in just design, period. The idea that, okay, we use some assumptions and some guesses to get a value, and they may be educated guesses and good rules to use. However, we still need to go through and verify that that design is good to go. Now, let me see. Okay. So, when we're analyzing the trial section, we're basically looking for 2 things. We're looking at PMN and we're looking at MU. And we want to verify that PMN is greater than or equal to MU. So that means we need to look at both sides of the equation. So let's look at MU first. It really doesn't matter which side you look at first. Just, I don't know, that's kind of what we did at the beginning of this problem. So let's go back to that. Now, in order to compute MU, we need a self-weight of the beam. Now, we assumed a self-weight earlier, but this self-weight is now going to change because the dimension changes. Now, remind me, if I have a beam that's B wide and H tall, how do I compute the self-weight? Oh, we did it. We did it in this problem. That's a calculation we're going to do a lot in here, so that's something you got to remember. If I want to determine the self-weight of a beam, what do? The unit weight times the area, right? Remember that? So because it's a rectangular section, gamma times B times H, okay? You kind of need to remember that because, I mean, we're going to be doing that quite a bit in here. So gamma times B times H. So that's 0, we're going to do it in kips. That's 0.15 kips per cubic foot. Remember, normal concrete, we're saying weighs 150 pounds per cubic foot or 0.15 kips per cubic foot. And then instead of those assumed dimensions, we're using the actual dimensions of the beam, 14 inches and 24 inches. Now, do I have something I need to do here? What do I got to do? Divide by 144, because 1 foot squared is 144 inches squared. So what does this come out to be? $0.350. Do I have a second on that? All right. Now, what are the units here? Kips per foot. Now, I want somebody to help me out. What did we get in step 1? What did we get for this value? 0.142. So during design, we assumed that the beam would weigh about 142 pounds per foot, but when we actually pick the section, it's like 350. So this beam is way heavier than we assumed. So when we look at our actual moment, it should be larger. So we'll say right here, I just want to indicate this is heavier than we assumed. So therefore, we can compute a new U, which is 1.2 times all the dead, plus 1.6 times our live load. Am I going too fast? Is everybody seeing where I'm getting these values from? This is just from the original part of the problem. Anybody got a value for me? $4.82. Do I have a second on that?
Yep.
So now we can use mu is WL squared over 8, so that's 4.82 kips per foot, 22 foot squared over 8. So it's going to equal something.
291.6.
291.6 foot kips. So let's just sort of write that down here, okay? So first I'll go ahead and second on that. Okay, so 291.6 foot kips. This is the actual self-weight. So by coming up with a more detailed estimate of the beam self-weight, the actual moment on it is higher than what we assumed. So I want you to just keep that in the back of your head for design purposes, because we're going to ask some questions about how this beam came, like what happened at the end. Okay, because I really want to sort of think about that. Okay, now that is this side of the equation. So we have mu on one side, but on another end we have phi mn. Okay, now you all should have enough experience with this. So you have the beam, you know what the beam looks like. Tell me what to do to compute phi mn. Like, tell me what we need to do.
Use that equation.
So mn, so hold on, so tell me what the equation is for mn.
I think it's ASFY B minus C over C.
You mean it's
Yes.
D minus C?
D minus A over 2.
There we go. D minus C, you're thinking of D minus C over C, that's the strain. Alright, so we're gonna, I know it's early, well, it's 10 o'clock, it's not that early. Come on. Alright, so we need to compute the nominal moment capacity, that's the expression. Do I know all of those quantities right now?
No.
What do I not know?
A.
A. Okay, so how do I compute A?
ASFY over 0.85. F prime C, B. Whatever.
So, whatever.
0.85. 0.85.
What's the whatever parameter? I'm messing with you. 0.85. Y'all laugh, I'm gonna call on somebody else next time. That's not right, they're laughing at you, Mr. Toller, that's just messed up.
I'm just trying to memorize.
Oh, you don't have to memorize, but now somebody else has to answer because they laughed at you. See, I'm looking out for everybody. Alright, so 0.85 times FC prime, which for this beam was what, 4 KSI?
Yeah. Yes.
Okay, alright, okay. Now what's B? Make sure everybody's paying attention. 14 inches. Remember, here we're using the actual dimensions. Remember, like we computed like a trial B value of like 8 1/4, but we're using the actual dimensions. Okay. Now, AS, what was the area of steel? What did it end up being?
3.82.
3.82, because we used 3 number 10. So 3.82 inches squared, and then 60 KSI. Remember, it was 60 KSI rebar. Okay, what does that come out to be? Say it again. 4.82 inches. Remember, it's inches. And so now we can use the MN formula, AS FY D minus A over 2. Now remember, these expressions for A and MN, they only work if the section is singly reinforced and if it's a rectangle. As soon as it becomes a triangle or a T-beam or a doubly reinforced section, all that goes out the window. So I'm just telling you all that now so that you're aware of that. Alright, so 3.82 square inches, 60 KSI. What was D for this section?
21.
21 inches minus 4.82 over 2. Now what does that come out to be?
4260.8.
Say it again, 4260.8. Okay, so 4260.8. What are the units there? No, they are not.
Inch kip.
They are inch kips because we have inches and kips. So now we want it to be in foot kips, and what do we need to do? Divide by 12. So that value divided by 12 is what?
355.1.
355.1. So there's that. Now we're not done, but we at least are looking pretty good, right? Why are we looking pretty good? Well, that's how much load we're putting on the beam, and that's how much it can hold up. Well, we can't use all of this because we have to reduce this by our resistance factor phi, right? So reducing it by our resistance factor phi means we need to determine phi. Now I get to call on somebody else besides Mr. Toller, all right, Mr. Adkins. If I want to determine the phi value, what's the first thing I need to compute?
We did it in MN.
Got him in, yes. Let me ask it another way. Phi is determined based on looking at what value? Like we look at what value to figure out what our fee value is going to be. You did that on the last homework. Say it again.
Strain.
The strain in the steel, right? Right? So we need the strain in the steel, okay? So, let's see. Mr. Clark, what is the expression for the strain in the steel?
That's a good question.
I know it's a good question. Now you did that on the last homework that you just turned in. Ms. Roberts.
Is it the 0.003?
There you go.
B minus C over C.
Exactly. Using that similar triangle expression. So do we know everything in that expression? Mr. Minot, you're shaking your head like no. What do we not know? We don't know C. And how do we determine C? A over beta 1. So what do you do? Okay, so first thing we need to do is C equals A over beta 1. Step 2, the strain in the steel is 0.003 B minus C over C. Boom. See? This isn't so bad. Alright, so I'm going to move on to the next panel. So C is A over beta 1, which is 4.82 inches over what? 0.85. And why is it 0.85? Because, well, not the normal weight. The weight doesn't matter for beta 1. What matters? The FC prime. Whenever FC prime is less than or equal to 4 KSI, beta 1 is 0.85. Remember, anytime your FC prime goes over 4 KSI, beta 1 goes down. Remember that? So, what does this come out to be?
5.67.
Do I have a second on that?
Yep.
Okay. Now, next thing we're going to do is we're going to compare that against the strain in the steel, which is 0.003 D minus C over C, which is 0.003, 5.67 inches. And what was D? 21 inches. And so what does that come out to be? And remember, strain values are really tiny. That's okay. So let's get specific. Let's do like 4 decimal places. 4 or 5, it doesn't really matter.
0.00811.
So 0.00811. Do I have a second on that?
Yep.
That's good. That's good. You want to be specific enough where you can make a determination. Okay. Now, what we do is we take our strain value and we compare that against some limiting strain value. Does anybody remember what the limit is? The strain at yielding plus 0.003. And how do we compute that? Fy over ES. So what we can do is we can say our limiting strain is Fy over ES plus 0.003. And so that's 60 KSI over what?
29,000.
That is right. That number will be burned into the back of your head by the time we're out of here. 29,000 KSI plus 0.003. And that equals what? 0.005. Do I have a second on that? I think it maybe comes up like 07 or something like that. But
From the slides, you said it 50.
yeah,
60 grade still, you assume.
I'm glad you remembered that. That is exactly right. I was getting ready to say that. That if you're ever dealing with grade 60 steel, this comes out to like 0.00507. So whenever you're dealing with grade 60 steel, so you could say the strain limit for grade 60, you can just take that to be 0.005. See, the spec actually used to have that as a constant for any steel. So, but now they're a little more refined with it. Okay, So I look at my strain in the steel and I compare that against the limit. And I can see that the strain in the steel is higher than the limit. So that tells me two things. First off, it tells me that I met the spec. The spec requires that the strain be higher than the limit. That's good to go. So because the strain is greater than the limit, that means ACI requirements met. What does it also mean?
Tension member.
Tension controlled member. Yeah. Well, and if it's tension controlled, so I can put tension controlled, but that means something else.
Fee equals 0.9.
There you go. Boom. Phi is 0.9. So now I know what MN is and I know what phi is. I can say that phi MN is 0.9 times, and I think MN was, what was it, 355.1? Was that right? 355.1 foot kips. And so phi MN is what?
319.6.
319.6 foot kips. So, here's some data for you. We had the assumed self-weight and the actual self-weight, but that assumed self-weight really doesn't matter so much anymore because all we care about is this. And so we just computed phi MN, and it came out to be 319.6. What can you tell me right now about our design? Is our design safe or unsafe? It's safe because the capacity, the usable capacity, is larger than the loads that are being applied to it. Now, if you're in steel design, let's see if you remember this, what could I do now to determine how good my design is? The efficiency calculation. So, if you're not in steel design, one of the measures that we use to determine the efficiency of our design is the load over the capacity. So 291.6 foot kips over 319.6 foot kips. And what this does is it's sort of like the Price is Right. We want this value to be as close to 1 as possible without going over. If it went over 1, if this, so first off, let's do the calculation here. So what does this come out to be?
91.2%.
So 0.912 or 91.2%. Now, if that value was over 1 or over 100%, it would mean that the numerator is larger than the denominator. And if the numerator is larger than the denominator, it would mean that the loads are more than the resistances. And if the loads are more than the resistances, what can you tell me about that design?
Being filled.
The beam fails, right? So we want that number to be as close to 1 as possible without going over. And so a good rule of thumb during design is if you can get that value to be like 90% or higher, you're doing pretty good. And in concrete design, I'll go ahead and tell you that you might be able to squeak by with 85% or higher, because sometimes when you're proportioning a beam, especially when you're looking at your rebar layout, there's only so many rebar patterns that work, and so you might end up getting a beam that's 88% efficient or 87% efficient, and that's fine too. But if you're 90% above, that's a really good design. That's a really efficient design. Sound good? Now, here's the pop quiz. There's one last thing we have to check. What's left? Not slenderness. No, that's steel design. That's steel design. I'll give you a hint. I told you that it probably isn't going to be that big of a deal, but we still need to check it. Mr. Minnock. There's one last check. You did it on last homework. What'd you do on the last homework that we haven't done here yet?
AS min.
The minimum area of steel requirement. We have to check and make sure that the steel pattern that we put in met AS min. Because remember, the spec says, I don't care what the capacity says, you've got to at least put this much steel in. So our final check is the minimum steel check. And so AS min is BD over FY times the max of 3 square root of FC prime, or 200 PSI. Remember that? Y'all did it on, hopefully you did it on the last homework assignment. I hope you did. So, 3 square root of FC prime is 3 square root of 4 KSI. There, I was waiting for somebody to say, that is wrong. You put in PSI, you get out PSI whenever you see a square root of FC prime. And so what is that? I'm not that good.
189.7.
189.7 PSI. So that is 14 inches, 21 inches, 200 PSI because it's the maximum, over 60,000 PSI. They have a value for me? 0.98, and what are the units? Square inches. And what was the actual area of steel that we used?
3.82.
3.82, so what can you tell me?
See.
That's good. So we've done a lot, and whenever you're doing design problems, there's a lot that you do. Like, you do a lot. So I always like at the end of the problem to put a little design summary. Just because, just because there's a lot of stuff we did. And I really think it's important that you get in this habit when you're doing homeworks and exams, because there's a lot going on and it's easy to miss stuff. So remind me, what was MU? 291.6. What was FEMN?
39.6.
So by looking at those two numbers, I can tell you the design is safe because FEMN is greater than or equal to MU. And from those two, efficiency was 91.2%. Okay? We know also two other things. ACI strain limit met, and we know that ACI minimum reinforcement limit met. Those were really the two key values that we had to check for our design. And so what is the answer? Here's the answer. The answer is use a beam with 3 number 10s. This dimension 21 inches. This dimension is 24 inches. This dimension is 14. And that's what the beam said, or that's what the problem said. Design the beam. Boom, there's the design. If this is going to be installed in a building and those are the loads on it, that's what you tell the contractor to build. All right, what do we think? Any questions about the process? Any questions about what we did? Any ways to, clarify things?
What do you use this, do we always assume we're using stirrups in our design?
That's a great question. Okay, so let's talk a little bit about that. So stirrups, let me say a couple things about that. Beams are going to have stirrups, just period. Okay? The reason for stirrups, and don't worry, we're going to spend a good bit of time on that later, but the reason for stirrups is for shear reinforcement. Everything that we're doing now, all we're looking at is the moment, but we haven't even talked about the shear. Okay? So if you were looking at this beam like on the side, so here's the beam, right? So this dimension is 24 inches. And if you wanted to give it some three-dimensionality, that dimension is 14, right? Does that make sense? Okay, so, and here's your support here, here's your support here. Okay, now, what we just designed, these three number 10s, those are the pieces of reinforcement that are running this way. On the bottom of the beam, because as I bend the beam, it's in smiley face bending, right? Okay? But that is not the only reinforcement. There will also be stirrups going like that, and they'll be like that, and so on and so forth. And so how to arrange those and to lay those out is something we are going to discuss. That's going to be like a homework 6 type thing. But they will be there because in most situations, the concrete's capacity to carry shear by itself is not enough. So you need that reinforcement. Now the big question is whether or not you're using number 3 stirrups or number 4 stirrups, because number 3s are really, really small. But it's not a matter of the size of the bar, it's about how far you space them. Like if you've got a lot of shear, well, you'll just need more of it. You know what I mean? So that's what you do when you design for shear, is you pick a stirrup and figure out how much you need it. So number 3s or number 4s are options that you can use. You could go bigger, but you'd have some serious shear load on that beam. So to answer your question, yes, we will pretty much always have stirrups in our beams. It's because of the shear. That's a great question. Any others? This is good stuff. All right, let's talk a little bit about design. What would happen if, let's take a look at these numbers. What would we do if that was the case? If that was the case, would our beam be safe or not? It would not be safe, right? Now, I want to look at this beam, and I want you to tell me, what could you do to this beam? What could you change in this beam to either change its capacity or improve its capacity, make it stronger? What parameters? So there's the beam. What could you do to make that beam stronger?
Increase the area of steel.
Okay, so number 1. The steel. Like you could up the steel or change the steel, and that's going to change the capacity. What else would change the capacity?
Increasing surface area,
The surface area. So what do you mean by that?
like the width or the depth.
Okay, so those are 2. There's B and D. Okay? There's 2 other parameters that we can change. What if I told you couldn't change that? The area of steel had to stay the same, the beam width had to stay the same, the beam depth had to stay the same. There's 2 more.
Actually brown.
There you go. What's the other?
The grade of steel.
Boom. Exactly right. Those are the parameters that are going to affect how strong the beam is. Okay? So, what if I told you I could show you in real time what that would do? Let me show you something. I want to look at this. Now, this is a spreadsheet that I wrote that what it will do is it will go through the calcs for this problem, and I wrote it just for this problem, but the spreadsheet is a bit smart in that what it will do is it will figure out, okay, if I change the area of steel, it will tell me whether or not the steel minimum reinforcement requirement has been met. Like for example, if I go here to the area of steel and I change it from 3.82 to 0.2, it tells me that the area of steel requirement has not been met. So it'll go through and smartly figure this stuff out, okay? Now, what I do is, okay, based on these values, I'm assuming that the height is the D plus 3 inches like we did before. It'll then compute a self-weight, a factored load, and a WL squared over 8 factored moment. It'll then determine it'll figure out what beta 1 needs to be based off of the concrete that you put in, then C, then the strain of the steel. It'll tell you whether or not that's fine. It'll also compute phi values for you, and then compute MN and VMN and do your efficiency check. So it basically does the whole problem for you. And the reason why I have this is because I want to show you what happens when you start tweaking values, okay? Because if you're the designer, I want you to have an understanding of what actually affects capacity and what doesn't, okay? Now what I'm going to do is I'm going to copy and paste these values sort of off to the side, because those are my defaults, okay? These are my default values. Now, one of the things to keep in mind, like for instance, if I take the beam and I make it twice as deep, like I want you to pay attention to the MU. Like if I make this 42, not only does it change the capacity, but it also changes the moment that goes on the beam, because if you made the beam twice as deep, you made it twice as heavy too. Does that make sense? All right. Okay. So I want to show you something. All right. So let's look at our baseline. Okay. So remember, here's our baseline. MU is 291.6 foot kips, and VMN is 319.6 foot kips. Okay. So let's say I wanted to make the beam stronger. Okay. Let's take a look at FC prime. FC prime is 4 KSI. What happens if I take FC prime and double it? Like what if instead of 4, what if I make that 8? Look what happens to VMN. Okay? See how VMN went from 319.6 to 340.3? Everybody see that? So think about it. I doubled the strength of the concrete. Did it really affect the strength all that much? Not really, you know. In fact, if you're doing reinforced concrete design, it's interesting how FC prime really doesn't matter all that much. I'm not saying it doesn't matter. I'm just saying in terms of actually generating an economical design, if you're the designer and you think, oh man, I got to make this beam stronger, doubling the compressive strength is really not going to affect your design all that much. So I would make that an uber last resort to say, well, I'm gonna up the FC prime. Now watch this. Okay, let's go back to our baseline. All right. Now watch this. Okay, so baseline, we have 319.6. Okay. Now I want to show you what happens with two things. Let's see what happens when you double the B value and you double the D value. Okay, let's take B and instead of 14, let's make it 28. Now what happened? Actually, hold on, wait. Let's make that 21. Okay, so originally this was 14, that was 21. Let's make the beam twice as wide and let's make it 28. Now what happened to the capacity? 340.3. It increased a bit, right? But not all that much. What happens instead? What if I keep that as 14, but I make this 42? Now look at the capacity. And see, I'm looking at the VMN value. Look at this. 680.6. So if you're the designer and you want to tweak the capacity, what has more power? Making the beam wider or making the beam deeper? Deeper. Think about it from this perspective. How do you compute the moment of inertia of a beam? or of a rectangle. It's BH cubed over 12, right? The height has a more direct impact on the beam's strength than the width. So if you take the beam and make it deeper, you're going to have a much more substantial impact on the beam's capacity than you are its by changing its width. Okay. Now I'll tell you one thing. If you really want to start tweaking a beam's capacity, I'll tell you. So let's go back to our baseline. If you really want to start tweaking a beam's capacity, you start messing with the steel. So for instance, the area of steel, if I double the area of steel, let's say, instead of 3.82, I mean, I didn't change the beam size at all, and just by throwing a few more bars in, it definitely starts jumping up something fierce. Same thing if I take the FY and I double it, if I make that 120. Now, changing the FY really does start messing with the beam's behavior a good bit, because you start getting some really weird values with the strains. And so because you've got this super monstrous amount of steel in there, it's like you almost have to make the beam bigger to counteract that. Like think, you have this monstrous amount of steel, so that you have to have enough concrete to provide enough force to counteract that. Remember, compression has to equal tension. So if you really start playing around with doubling your steel and making your steel, oomphed up, you can really start getting a weird design. I mean, going back to the original, like 60 and 3.82, I mean, if all I do is just take that and make it 5, the efficiency went from 90-some percent to 72%. That's just like one more bar. One more bar can reduce the efficiency of that beam by like 20%. So if you need to increase the capacity, just a little bit of steel can make a lot of difference. Okay? Yes, sir.
What would you do if you had certain parameters for like the height and the base? Like that was your max you could do for the bar.
That is a fantastic question. Okay? That's a fantastic. So the question was like, what if the architect says no, the beam can't be deeper? Okay? And you do the design and it's not enough. Okay? What do you do? Well, let's consider that this was a building, right? So here's the columns, here's the floor, here's the next column, and you're designing beams to support that floor system, right? And let's say, okay, I have tried everything I can do. I cannot go past that depth because the architect told me I can't. I looked at the loads, it's still not enough. Now, I kind of lied here because there's a sixth thing that you can kind of change. Now, let me ask you this. If I can't change what the beam looks like, if I want to produce a safe design, what could I change? I can't change what the beam looks like. If I can't change any of this. All of this is all about PMN. What's the other side of the equation?
Just add more of them.
That's exactly right. See, I can't change the loads directly. But what I could do is, look at this. I've got 3 beams. Maybe what I do is I have 4 beams. What would that do? That would decrease the tributary width for each beam. If I decrease the tributary width for each beam, that decreases the amount of load that each beam is responsible for. So instead of trying to up the capacity, maybe what I try and do is decrease the loads by adding more beams. And so that's an option as well. Are there advantages and disadvantages to that? I mean, obviously, but I mean, load demand's load demand. Now, what you probably can't do is say, well, this floor has 80 PSF. No, it can only have 60. Because then you're starting to tell the architect, you can't use this for an office building. It can only be a hospital. I'm designing an office building. It's got to be an office building. So the loads are the loads. That's like the concept, that's what the building's being used for. Does that make sense? Any questions? This is good stuff. Is this better than x equals 4? I hope it is. All right, we're actually out of time, So we're going to cover the known cross-section next time, but I want to give just like a taste of it. When you're designing a known cross-section, there's really only one independent parameter, and that's the area of steel. This is what you don't know. Because when you have a known cross-section, so if you're dealing with a slab design or a precast shape, you actually know what the beam looks like, so you're just solving for the area. Now what we do with design is we treat it very, very much like what we did with the last problem, and we made use of reinforcement ratios. The difference though is that with this expression, we derived this expression earlier. What we did last time is we said, well, let's look at this equation and see if we can solve for BD squared. Well, if we know what B is and we know what D is, why don't we solve for the reinforcement ratio? And so what you end up getting, doing a little bit of algebra, is you get this expression here down below. And so before, we just guessed a reinforcement ratio and used that for design. Now that we know what the beam looks like, now we just solve for the reinforcement ratio. We solve for how much reinforcement we need, and we design the beam that way. So this problem is much simpler and it's much shorter. You don't have to assume the beam self-weight because you know what the beam looks like. The only thing you have to assume is that P equals 0.9, and then pick a reinforcement pattern that meets your load demand. So it's a lot faster, it's a lot quicker of a problem. So we'll do that pretty quickly, and then we'll go into slab design. And you know, look, and the idea is, okay, if I look at a typical floor system, I got beams, girders, and slabs in between. So the idea is when we're done, you can design the whole floor system. That's all I got. I will see you all on Friday. Don't forget your homework. Actually, I'll see most of you here in about 10